A breakthrough for scientists after they had a 20-minute conversation with a humpback whale.
A researcher at MIT stares at her screen. The room is silent except for the hum of servers. On her monitor, 9,000 recordings of sperm whale clicks, fed into the same class of deep learning AI that powers ChatGPT. The results load. She leans forward, and then she whispers 4 words out loud. This isn't supposed to be possible. Because what the AI just found wasn't random noise from an animal. It wasn't a simple set of warning calls or feeding signals. It was a phonetic alphabet, complete with vowels that look structurally identical to the building blocks of human speech. Not similar. Identical. And nobody in that room has an explanation for how that is possible. For decades, the science of sperm whale communication was considered settled. Sperm whales communicated using short, rhythmic bursts of clicks called codas. Researchers had cataloged roughly 21 distinct coda patterns. Each one carried a fixed, simple meaning: a warning, a direction, a contact call. Scientists essentially treated whale communication like a traffic light. A small number of states, a fixed set of meanings, no real complexity. It was Morse code from the deep sea, and science thought it had already cracked it. That assumption wasn't just wrong. It was one of the most spectacular miscalculations in the history of modern biology. The story of how it collapsed starts with a marine biologist, a passing cryptographer, and a conversation that nobody planned. David Gruber was a biologist at the City University of New York, sitting in his office at Harvard's Radcliffe Institute, reviewing sperm whale recordings he had collected while studying jellyfish in the Caribbean. The sounds were what they always were: rapid-fire mechanical clicking, like Morse code played underwater. He had heard them 100 times. Background noise from an animal he assumed science had already figured out. MIT cryptographer Shafi Goldwasser was walking past his open door. She stopped. She listened. Then she said, "That sounds like Morse code. Have you tried using machine learning to decode it?" Gruber hadn't. Nobody had. Goldwasser had spent her career cracking actual encrypted communication systems, the kind governments use to hide state secrets. Her instinct wasn't casual curiosity. It was professional pattern recognition. To someone who cracks codes for a living, those whale clicks weren't animal noise. They were a cipher that had never been run through a decoder. That conversation led to a third person, Michael Bronstein, an AI researcher who explained that the same deep learning algorithms powering large language models could, in theory, be applied to animal communication, as long as researchers gathered enough data. That was 2020, and it became the founding moment of Project CETI, the Cetacean Translation Initiative. Project CETI is not a modest research project. It was funded by the TED Audacious Project with partnerships from MIT, Harvard, UC Berkeley, and 15 other institutions. And from the beginning, it was designed to do one thing no previous whale study had ever seriously attempted: gather data at the scale and depth required to feed a serious AI. The team established a permanent research station on the island of Dominica, a stretch of Caribbean water where multi-generational sperm whale families have been observed for decades. These are not anonymous animals. Individual whales are known by name. Social hierarchies have been mapped. The matriarchs are identified. Then the team built the instrumentation around them. Hydrophone arrays were permanently installed along migration routes. Biologger tags, engineered at Harvard School of Engineering, were developed to attach directly to whale skin via suction cup. Each tag carries 3 synchronized microphones capable of distinguishing individual voices in a group conversation, alongside GPS logging, depth sensors, and accelerometers tracking body movement to within fractions of a degree. In 2025, the team unveiled a new tap-and-go drone-based method to tag whales, a racing drone approach that makes tagging faster and even less invasive. The system was designed to capture not just what the whales said, but who they were saying it to, what they were physically doing at that moment, and what was happening acoustically around them. Every variable that could give meaning to sound was being logged simultaneously. 9,000 recordings, fed into deep learning AI, and what came back rewrote the textbooks. The AI didn't find 21 codas. It found 156, but the number is almost beside the point. What mattered was what was inside them. Each coda has internal structure, tempo variations, rhythm shifts, and what researchers call ornamentation clicks layered in recurring patterns. These elements aren't decorative, they're functional. They work the way phonemes work in human language. Modular units combined according to rules to generate meaning that no single unit carries alone. The whales were not transmitting 156 preset messages like a fixed menu. They were constructing communication dynamically from a modular phonetic system, the same fundamental architecture that underlies every human language ever documented on Earth. Here's an analogy that makes this concrete. English builds millions of words from just 44 basic sounds. Remove one sound and thousands of words vanish. Add a rule about how two sounds can combine and new words become possible. Sperm whales appear to operate on exactly the same principle. A finite acoustic inventory producing a generative system with effectively unlimited expressive range. MIT's Dr. Daniela Roos described the findings simply, "Our results show there is much more complexity here than previously believed. This is challenging the current state-of-the-art of beliefs about the animal world." That is the most understated sentence in modern science, because nothing about what the AI found was a small adjustment. It was a structural demolition of the assumption that nothing in the animal kingdom had ever independently evolved anything resembling the architecture of human language. Except something had. And it had been doing it in the dark, a mile underwater, for 30 million years. Then came the finding that made an entire scientific field shudder. UC Berkeley linguist Gasper Begusch, the linguistics lead at Project CETI, ran a separate analysis. Instead of mapping coda patterns at the sequence level, he examined the acoustic properties of individual clicks at the most granular resolution available to modern phonetics equipment. Using generative adversarial networks, machine learning models that identify patterns by learning to imitate them, Begusch discovered something that, if you have any background in linguistics, should stop you cold. The whales were producing vowel sounds, specifically the ah vowel, the a in father, the ee vowel, the e in see, and diphthongs, those gliding double vowel combinations like the oi in boy. Begusch described it plainly. In the past, researchers thought of whale communication as a kind of Morse code, but this paper shows their calls are more like very, very slow vowels. This suggests a complexity that approaches human language. Read that carefully. Complexity that approaches human language. From a species that developed its communication system in complete darkness, under thousands of pounds of water pressure, along a completely independent evolutionary path, with no shared ancestor with humans for hundreds of millions of years. Vowels are not a simple category of sound. They are precise, controlled modulations of frequency through specialized vocal anatomy, the kind that requires an evolved larynx, specific musculature, and the neural capacity to control it with intention. That combination was considered uniquely human, a product of evolutionary pressures specific to our lineage, in our environment, over our timeline. Sperm whales arrived at the same solution from a completely different starting point. They evolved towards something that, when analyzed by the most advanced acoustic equipment available, looks functionally identical. That's not a parallel. That's convergent evolution. Two separate lineages arriving at the same complex solution through entirely different routes. And when it happens with something as specific as vowels, the only interpretation that makes sense scientifically is this: vowel-based communication is not an accident of human anatomy. It is a feature of intelligence itself. Structure is one thing, but the whales don't just possess these components in isolation. They use them contextually, and that distinction is everything. The same individual whale produces different codas depending on who it is addressing, what the other whale just said, and what is happening in the immediate environment. That is not a signal system with fixed inputs and fixed outputs. That is pragmatic language use, the ability to deploy communication responsively, in real time, adjusted to a shifting social situation. Shane Garrow has spent 13 years alongside sperm whale families in Dominica. He describes watching these interactions unfold from the surface. It is hard not to see cousins playing while chatting, to not see a mother hand her calf to a babysitter and exchange what looks for all the world like a few parting words before diving deep to hunt. The exchanges last up to an hour. Multiple whales overlap, respond, build on each other's contributions. There is measurable conversational timing, rhythm, and turn-taking that occasionally breaks down when two whales click simultaneously, which Jarrow notes appears to be socially acceptable in sperm whale culture, the way interrupting can be among close family. Consider what that actually requires from a brain. To produce the right coda for the right whale in the right moment requires not just memory and acoustic control. It requires a theory of mind, an awareness that the other individual has a perspective different from your own, and that what you say should be calibrated to reach them specifically. That capacity was once considered uniquely human. The brains sustaining those conversations are the largest of any animal on Earth. 6 times the mass of a human brain. Sperm whales live in matrilineal families with multi-generational social structures, cultural traditions transmitted from grandmother to mother to calf across centuries, and coordinated deep-water hunting strategies executed in pitch darkness across hundreds of meters of open ocean. Here is where honesty matters. The AI has mapped the grammar. It has not translated a single word. Structure is not meaning. The phonetic inventory has been identified. The combinatorial rules have been modeled. The vowels have been cataloged. The conversational patterns between family members have been documented across years of recording. All of that is real, verified, and peer-reviewed. What remains completely unknown is what any of it encodes. What does a specific coda sequence mean? What is the difference in content between a rising tempo pattern and a falling one? What does it mean when a matriarch addresses the whole group versus when a mother clicks at length to her calf? Nobody knows yet. Project CETI is not entering this conversation as translators with a finished dictionary. It is entering as students who have just learned the alphabet, trying one behavioral correlation at a time to figure out what the words mean. And every hour of new recording makes the dictionary slightly less blank. In the 1960s, researchers Roger Payne and Scott McVeigh proved humpback whales sing complex, evolving songs. Before that, most people thought of whales as large, commercially valuable marine animals, ecologically present, but not cognitively significant. That single finding sparked the Save the Whales movement and led directly to the Marine Mammal Protection Act, pulling multiple species back from the edge of extinction. One discovery about whale intelligence rewrote international conservation law. Proving sperm whales have language, not songs, not signals, but a compositional linguistic system with vowels, phonemes, and grammar could make that look modest. Legal scholars are already asking what follows. Project CETI has partnered with New York University School of Law's More Than Human Life program to explore the legal implications. A 2024 treaty among Indigenous peoples from New Zealand and the Cook Islands, the He Wakaputanga Moana Declaration, has already recognized whales as legal persons with specific rights. Meanwhile, the environmental stakes are already urgent. Sperm whales navigate and communicate in a world where sound replaces sight. Underwater noise pollution from industrial shipping, military sonar, and deep-sea mining doesn't just disrupt them, it floods their acoustic environment with interference. Chronic exposure disorients whales, drives them from feeding grounds, and causes physical harm. At higher intensities, the noise can cause permanent hearing loss. If that community speaks a language, then the industrial noise filling every ocean basin isn't just environmental damage. It's something closer to the systematic destruction of a culture's ability to communicate. A sperm whale can live 70 years. The matriarch of a family alive in the Caribbean today may have been born before sonar existed. She has spent her entire life communicating with her family in a system that science only just admitted might be language. Whatever she has said across those decades, whatever knowledge she transmitted, whatever warnings she issued, whatever she told the young ones about how the world works, all of it happened in a language we could not read. These whales have watched the ocean change in ways no human has documented from the inside. They have lost family members to ships they could hear coming and could not escape. They have watched the acoustic environment they depend on become increasingly saturated with the noise of a civilization that never paused to wonder if anyone was listening back. If they have language, and the evidence now says they do, then they have been talking about all of this. They have been talking about us. The alphabet has been found. The vowels have been identified. Project CETI is building an open-source platform to share its entire data set with the global research community, because they know that when the first full sentence surfaces, this moment will belong to everyone. We don't know yet what it says, but for the first time in human history we are finally learning how to listen. Subscribe, because the moment Project CETI decodes the first full sentence, you'll want to be here when it surfaces.